When calculating branch circuit conductor ampacity for air conditioning units with single motor compressors, it is crucial to understand the requirements outlined in the National Electrical Code, specifically NEC 440.32. This section addresses the sizing of conductors for such equipment to ensure safe and reliable operation. NEC 440.32 states that the branch circuit conductors supplying a single motor compressor must have an ampacity not less than 125% of either the motor compressor rated load current or the branch circuit selection current, whichever is greater. This 125% rule is essential because it provides an additional safety margin to account for the motor's potential to draw more current during startup or under certain operating conditions. To clarify the application of this rule, firstly, identify the motor compressor rated load current and the branch circuit selection current. These values are typically found in the equipment's nameplate or in the manufacturer's specifications. The motor compressor rated load current represents the current the motor is expected to draw under normal operating conditions. The branch circuit selection current, on the other hand, is a value determined by the manufacturer, which may be higher than the rated load current to account for specific application requirements. Secondly, determine which of these two values, the motor compressor rated load current or the branch circuit selection current, is greater. Once you've identified the larger value, multiply it by 1.25 to obtain the minimum required ampacity for the branch circuit conductors. For instance, if the motor compressor rated load current is 10 amps and the branch circuit selection current is 12 amps, you would use 12 amps as the basis for your calculation. 12 amps multiplied by 1.25 equals 15 amps. Therefore, the branch circuit conductors must have an ampacity of at least 15 amps. Thirdly, select conductors with an ampacity that meets or exceeds the calculated value. Consult the appropriate ampacity tables in the NEC, such as those found in Article 310, to determine the correct conductor size based on its insulation type, temperature rating, and installation conditions. It is important to consider factors such as ambient temperature and the number of conductors in a raceway or cable, as these can affect the conductor's ampacity. Fourthly, consider the exception where nameplate values can be used directly. NEC 440.6 addresses the use of nameplate values for calculating conductor ampacity. According to this section, you can use the nameplate values directly only if they are equal to or greater than 125% of the motor compressor rated load current or the branch circuit selection current. In other words, if the manufacturer has already accounted for the 125% factor in the nameplate value, you do not need to apply it again. However, it is crucial to verify that the nameplate value actually reflects this increased ampacity. To ensure compliance with the NEC and to avoid potential safety hazards, follow these steps carefully when calculating branch circuit conductor ampacity for single motor compressor air conditioning and refrigerating units. Firstly, obtain the motor compressor rated load current and the branch circuit selection current from the equipment's nameplate or manufacturer's specifications. Secondly, compare the two values and identify the larger one. Thirdly, multiply the larger value by 1.25 to determine the minimum required ampacity for the branch circuit conductors. Fourthly, select conductors with an ampacity that meets or exceeds the calculated value, considering factors such as insulation type, temperature rating, and installation conditions. Fifthly, only use nameplate values directly if they are equal to or greater than 125% of the motor compressor rated load current or the branch circuit selection current. In summary, the NEC 440.32b mandates using 125% of the larger value between the motor compressor rated load current and the branch circuit selection current for calculating branch circuit conductor ampacity. The nameplate values can be directly applied only when they are equal to or exceed this 125% threshold. Understanding these requirements is essential for ensuring the safe and efficient operation of air conditioning and refrigerating equipment while complying with electrical codes. The 125% rule is not arbitrary. It is designed to address several factors that can influence the current draw of a motor compressor. Firstly, motor starting currents can be significantly higher than the rated load current. When a motor starts, it experiences a brief period of inrush current, which can be several times higher than its normal operating current. This inrush current can stress the conductors and over time can damage the insulation if the conductors are not adequately sized. By providing a 25% margin of safety, the 125% rule helps to ensure that the conductors can withstand these temporary overcurrents without overheating or experiencing premature failure. Secondly, operating conditions can affect the current draw of a motor compressor. Factors such as changes in ambient temperature, variations in the cooling load, and fluctuations in voltage can all cause the motor to draw more current than its rated load current. The 125% rule provides a buffer to accommodate these variations and prevent the conductors from being overloaded. Thirdly, the 125% rule helps to prevent nuisance tripping of overcurrent protection devices, such as circuit breakers or fuses. If the conductors are sized too close to the motor's rated load current, even small increases in current draw can cause the overcurrent protection device to trip, interrupting the power supply to the equipment. By providing a margin of safety, the 125% rule reduces the likelihood of nuisance tripping and ensures that the equipment can operate reliably. When selecting conductors for an air conditioning unit, it is also important to consider the voltage drop in the circuit. Voltage drop occurs when the voltage at the load end of the circuit is lower than the voltage at the source end. Excessive voltage drop can cause the motor to operate inefficiently, overheat, and even fail. To minimize voltage drop, it is generally recommended to size the conductors larger than the minimum required by the NEC. The NEC provides guidelines for voltage drop in Informational Note number 2 to NEC 210.19a on, recommending a maximum voltage drop of 3% for branch circuits and 5% for feeders. To calculate voltage drop, you can use the following formula: voltage drop equals 2 times K times I times D divided by Cm, where K is the direct current constant, typically 12.9 ohms circular mils per foot for copper and 21.2 ohms circular mils per foot for aluminum. I is the current in amps, D is the one-way distance of the circuit in feet, and Cm is the circular mils area of the conductor. For example, let's say you have a 20 amp load that is located 100 feet from the source and you are using number 12 American wire gauge copper conductors, which have a circular mils area of 6,530 circular mils. Using the formula, the voltage drop would be 2 times 12.9 times 20 times 100 divided by 6,530, which equals approximately 7.9 volts. If the source voltage is 120 volts, the voltage at the load end of the circuit would be 120 volts minus 7.9 volts, which equals 112.1 volts. This represents a voltage drop of 6.6%, which exceeds the recommended maximum of 3% for branch circuits. To reduce the voltage drop, you would need to increase the size of the conductors. In addition to conductor ampacity and voltage drop, it is also important to consider the grounding requirements for air conditioning units. The NEC requires that all electrical equipment be properly grounded to provide a safe path for fault current to return to the source. This helps to protect people from electric shock and to prevent damage to equipment in the event of a ground fault. The grounding conductor must be sized in accordance with NEC Table 250.122. Which specifies the minimum size of the grounding conductor based on the size of the overcurrent protection device. For example, if the overcurrent protection device is rated at 20 amps, the minimum size of the grounding conductor is number 12 American wire gauge copper. It is also important to ensure that the grounding conductor is properly connected to the equipment and to the grounding electrode system. The grounding electrode system typically consists of a ground rod, a metal water pipe, or a concrete encased electrode. The grounding electrode system must be properly bonded together to create a low impedance path for fault current. In summary, when calculating branch circuit conductor ampacity for air conditioning units, it is essential to comply with the requirements of the NEC, specifically NEC 440.32. This section requires that the conductors be sized at not less than 125% of the motor compressor rated load current or the branch circuit selection current, whichever is greater. This rule provides a safety margin to account for motor starting currents, operating conditions, and voltage drop. It is also important to consider the grounding requirements for air conditioning units to ensure electrical safety. By following these guidelines, you can ensure that the air conditioning unit operates safely and reliably while complying with the NEC. Let's consider a more detailed example to further illustrate the application of NEC 440.32. Suppose we have an air conditioning unit with a single motor compressor. The motor compressor nameplate indicates a rated load current of 15 amps and a branch circuit selection current of 18 amps. To determine the minimum required ampacity for the branch circuit conductors, we need to compare these two values and select the larger one, which in this case is 18 amps. Next, we multiply 18 amps by 1.25, which equals 22.5 amps. This means that the branch circuit conductors must have an ampacity of at least 22.5 amps. Now, we need to select conductors that meet or exceed this ampacity rating. Consulting NEC Table 310.16, which provides ampacity ratings for various conductor sizes and insulation types, we can see that number 12 American wire gauge copper conductors with THHN insulation, which has a temperature rating of 90 degrees Celsius, have an ampacity of 30 amps when installed in a raceway with no more than 3 current carrying conductors. Since 30 amps is greater than the required 22.5 amps, number 12 American wire gauge THHN conductors would be suitable for this application. However, it is important to note that the ampacity ratings in NEC Table 310.16 are based on specific conditions, such as an ambient temperature of 30 degrees Celsius and no more than 3 current carrying conductors in a raceway. If the actual conditions differ from these assumptions, it may be necessary to adjust the ampacity rating accordingly. For example, if the ambient temperature is higher than 30 degrees Celsius, the ampacity of the conductors must be derated to account for the increased heat. Similarly, if there are more than 3 current carrying conductors in a raceway, the ampacity of the conductors must be derated to account for the increased heat generated by the conductors. Derating factors are provided in NEC Table 310.15b3 for ambient temperature correction and NEC Table 310.15b3 for adjustment factors for the number of current carrying conductors in a raceway or a cable. Let's assume that in our example, the ambient temperature is 40 degrees Celsius. According to NEC Table 310.15b3, the correction factor for THHN conductors at an ambient temperature of 40 degrees Celsius is 0.91. This means that the ampacity of the number 12 American wire gauge THHN conductors must be multiplied by 0.91 to account for the increased ambient temperature. 30 amps multiplied by 0.91 equals 27.3 amps. Since 27.3 amps is still greater than the required 22.5 amps, number 12 American wire gauge THHN conductors would still be suitable for this application, even with the derating for ambient temperature. However, if there were more than 3 current carrying conductors in the raceway, it may be necessary to use larger conductors to compensate for the additional derating. In addition to conductor ampacity, it is also important to select the appropriate overcurrent protection device for the branch circuit. The overcurrent protection device, such as the circuit breaker or fuse, is designed to protect the conductors from overloads and short circuits. The NEC specifies the maximum allowable overcurrent protection for different conductor sizes in NEC Table 240.4b. For example, for number 12 American wire gauge copper conductors, the maximum allowable overcurrent protection is 20 amps, unless otherwise permitted. This means that in our example, we would need to use a 20 amp circuit breaker or fuse to protect the number 12 American wire gauge THHN conductors. It is important to note that the overcurrent protection device must be sized to protect the conductors, not the equipment. The equipment may have its own internal overcurrent protection, but this does not replace the need for branch circuit overcurrent protection. The branch circuit overcurrent protection is designed to protect the conductors from overloads and short circuits, while the equipment's internal overcurrent protection is designed to protect the equipment itself. Finally, it is important to follow all applicable codes and standards when installing electrical wiring for air conditioning units. The NEC is the primary code that governs electrical installations in the United States, but there may also be local codes and standards that apply. It is important to be familiar with all applicable codes and standards to ensure that the electrical installation is safe and compliant. In addition to the NEC, there may also be industry standards that provide guidance on best practices for electrical installations. For example, the National Electrical Contractors Association (NEC) publishes a variety of standards and guidelines for electrical installations. Following these standards and guidelines can help to ensure that the electrical installation is performed correctly and safely. By carefully considering all of these factors, you can ensure that the electrical wiring for air conditioning units is properly sized, protected, and installed in accordance with all applicable codes and standards. This will help to ensure that the air conditioning unit operates safely and reliably for many years to come.